on Fourier transform. So last time we were doing, so we finished everything? Or?
We were still working through the solution for Pn parabolic wave.
All right, so we have parabolic wave, Fx will be x, 1 minus x, when x is from 0 to 1, and x, 1 plus x, when x is from minus 1 to 0. All right, this is the parabolic wave. Parabolic wave. So for the last time we computed A0 and this is 0. For AN this is 0. For BN, so I remind you that A0 will be 1 over 2 of e to over minus 1 to 1 of Fx dx. AN will be 1. So here we don't have L, so this is the interval from minus 1 to 1 of Fx cosinus of n pi x dx. And Bn will be the sinus, right? Sinus of n pi x dx. So last time we were trying to compute Bn, which is integral from minus 1 to 1 of Fx sinus of n pi x dx. And because last time we said that this is even function, odd function, so we're gonna have x minus x squared sinus of n pi x dx. All right. So right. Thank you.
Thank you.
Right. So let me explain again. Last time we was trying to compute a Fourier series of the parabolic wave, in which the function is defined to be x, 1 minus x, when x is going from 1 to 0, and it is x1 plus x when x is going from minus 1 to 0. So this is a 2 periodic function. So in other words, we don't have to consider function outside of the interval minus 1 to 1. Right? So minus 1 to 1 is the interval that we want to study. So last time, we know that A0 is 0, AN is 0, in which A0 is the interval from minus 1 to 1 of Fx dx, and we divide by 2. AN will be the interval from minus 1 to 1 of Fx cosinus n pi x dx, and Bn is the interval from minus 1 to 1 of Fx sinus n pi x dx. All right, so now let us try to compute Bn. So Bn will be, because here we have an even function, so I only need to compute the value of the interval from 0 to 1, and I multiply that by 2, because the interval on the minus side and the interval on the plus side are the same. So last time we were trying to do this, and this is integration by part, right? So we have x minus square. So last time we tried to find a function. We tried to use the interval u dv is uv minus v, the interval of v du. So this is integration by part. All right. In this case, u is going to be x minus x squared, and v is going to be, so dv will be sinus of n pi x dx, which means that v will be the antiderivative of the function sinus, and we know that v will be cosinus of n pi x of n pi with a minus. All right? So we apply integration by part to this guy, and we have 2 times uv, which is x minus x squared cosinus of minus cosinus of n pi x over n pi, and take the difference between 0 and 1, right? And this guy is 0. So the second one will be plus integral from 0 to 1 of cosinus of n pi x over n pi. All right? And then I have to take the du, which is so here du will be computed by taking the derivative of this guy. So du, I'm gonna replace that by 1 minus 2x dx. All right? It's good. So to compute the second term, I'm gonna split it into two integrals. So the first one will be the integral from 0 to 1 of cosinus n pi x over n pi dx. So last time we know that this is 0, right? And the second one will be minus 2 times integral from 0 to 1 of cosinus of n pi x over n pi x dx. It's good? So this is where we stopped last time. All right, so I explain again. Now, I'm gonna compute Bn by taking the integral from minus 1 to 1 of fx multiplied with the sinus n pi x dx, all right? Because this is an even function, so I'm gonna combine both of them. I'm gonna have to compute the integral only on the positive interval, which is from 0 to 1, and I multiply that by 2 because the integral on the positive side and the integral on the negative side are equal. Now, to compute this interval, I'm going to use integration by part. The formula of the integration by parts will be u dv is uv minus v du. All right, in this case, u will be x minus x squared, dv will be sinus n pi x dx. So v will be the antiderivative of the sinus, which is the minus of cosinus, and of course I have to remember to divide by n pi, which is the factor. All right, so the uv will become this guy. This is uv, right? But when I evaluate this difference, I'm going to get 0. The second thing is the integral of v du. So I have cosinus n pi x over n pi, and du will give me the derivative of this guy, which is 1 minus 2x dx. All right? So this is du. All right? Again, I'm going to split this into two integrals. The first one is the cosinus dx. This is 0. The second one is minus cosinus n pi 2x, but I'm going to put 2 outside, and I'm going to put n pi outside. Now I have to compute. So this is going to be 0, and this is going to be 0. So the leftover is just this guy. All right? Now I have to compute this one. So I have integral from 0 to 1 of cosinus n pi x dx. All right, so we know that for this one we have to use integration by part again. All right, so I'm gonna put x here. So this is u and this is dv. All right, so this u will be x, and dv will be cosinus n pi x dx, which means that v has to be the antiderivative of cosinus, which is sinus n pi over n pi. All right. So a reminder: sinus of x prime will be cosinus, but cosinus of x prime will be minus sinus. All right. So this is why here I have a minus, and here I don't have any minus. All right. So this is the formula that we need to keep in mind. It's clear? Questions? Right. So now I'm gonna use integration by part again. So this gives me uv, which is x sinus of n pi x over n pi, and I evaluate at 0 and 1. When this is 0, sinus is 0, and when this is 1, sinus is also 0. So this is going to be 0, right? So the left hand side will give me integral from 0 to 1 of v du, which is sinus of n pi x over n pi dx.
What happened to the 2 over n pi?
I I compute the integral first and I go multiply by that later. All right? So here I have u dv, which is cosinus n pi x dx. So I'm going to take the antiderivative of cosinus and I get sinus. So I use the integration by part. The first part is going to be 0. All right? And the second part will give me minus of 1 over n pi, integral from 0 to 1, sinus of n pi x dx. All right? So this will give me 1 over n pi squared cosinus of n pi x, and I evaluate at 0 and 1. All right? So what is cosinus of n pi 1? Yes? Right. So here I'm going to have 1 over n pi squared. Right, so here I have cosinus of n pi 1 minus cosinus of 0, right? So this is negative 1 to power n, all right? So this gives me 1 over n pi squared, negative 1 to power n minus 1, all right? So I replace it here. I'm gonna get minus 2 over n pi to the power 3 minus 1 to the n minus 1. Now let us explain again this computation. All right. Now, so this is where we stopped last time. We remove this guy, and the leftover is this integration, right? I'm gonna compute this integration. I have x cosinus n pi x dx. This is going to be my u, and this is going to be my dv. I'm gonna use integration by part. So u is x, and dv should be cosinus n pi x dx. All right. Which means that v should be the antiderivative of cosinus n pi x, which is sinus n pi x over n pi. Right, so now I'm going to use integration by part. I have uv, which is this guy. So I have x sinus n pi x over n pi. I take the difference between 0 and 1. This is going to be 0, because when I replace 1 here, sinus of n pi is 0, and when I replace 0 here, sinus of 0 will be also 0. So this is going to be my v du, all right? I have minus the integral from 0 to 1 of v, which is sinus n pi over n pi du, which is dx. All right? I put minus n pi outside. So I have the integral from 0 to 1 of sinus n pi x dx. The antiderivative of sinus n pi x is minus cosinus, but I have a minus here, so I don't have to. I can just write cosinus, and of course I have to divide by n pi. So here I have a square. Now I take the difference between 0 and 1. This gives me cosinus n pi of 1 minus cosinus of 0. So cosinus n pi will give me minus 1 to the power n, and the other one will give me 1. All right? So I replace this here, and I get minus 2 n pi cubed minus 1 to power n minus 1. Yes?
I got 4 over n pi cubed because we're going off of this as an even function, so we already are multiplying it by 2.
Yes, we have to multiply
and then we
by 2.
slip another 2 in there, but at the bottom it looks like
It's going to be 4, right?
that's what I got, but I don't know if it's
Right. So here I yes. So here we have to have a number 4 propagate here. Right. And here I have a number 4, and here I have a number 4. So here I should have a number 4. Can you say at the back of the paper, please? Thank you. Right. So I miss a number 2, which is here. So the final result has to be minus 4 over n pi cubed minus 1 to power n minus 1. And so I can combine the 2 minus. I have 4 over n pi to the power 3 and 1 minus 1 to power n. All right? It's clear? So previously I forgot the number 2. So we have to put the number 2 here. So I have the number 2. But here I have minus, and here I have minus 1 to power n minus 1. So I multiply minus inside I have 1 minus 1 to power n. Questions? It's clear? Yes?
So the step from the 2, the step up, no, down. Yeah, so you just separate the 1 minus the 2x.
Yes, so I separate 1 minus 2x.
Okay, but you could also do the integration by parts again, right?
Yes, I can do integration by part again. This is the same.
Okay.
But here it's easy because when you separate them, the first one will be 0. So so when you separate, it's simpler because it's 0.
Okay.
Right. Other questions? It's clear? All right. So now let us. So in this case, we have what? We have 4 over n pi to the power 3. 1 minus 1 to the power n. All right. Now let us write out the form of the Fourier transform. Right, so fx will be a0 plus the sum when n is going from 1 to infinity of an cosinus of n pi x plus bn sinus of n pi x. Right? I want to check it. Alright, so this is the general form of the Fourier series. You have an a0 plus the sum when n is going from 1 to infinity of an cosinus n pi x plus bn sinus n pi x. We're going to replace all of the values that we found here, so an should be 0. So here a0 is 0, an should be 0, so I have the interval from n is going from 1 to infinity of 4 over n pi to the power 3, 1 minus 1 to the power n of sinus of n pi x. All right? It's clear? So what you can do is that you can write the parabolic wave in terms of a series, of a sum of a series of the sinus function, right? Here I0 is 0 and an is 0. So we don't have the function cosinus, right? So because this is 0 and this is also 0. All right? It's clear? Now let us look into this series, and that is going to we will see that this series is important in the sense that we will understand. We can solve partial differential equation about real value problems using Fourier series. Suppose that I want to take the derivative in terms of x of the function f. What should I do? Yes?
You plug in all the n's and to 1 to infinity, sum them up, and then you take the derivative with respect to x.
So I don't understand. So
You plug in from n equals 1 to a certain number, infinity, and then you take the derivative
of what?
with respect to x.
Right.
The function.
Right. But here I have sinus, right? So how can I take the derivative? Any other side? Yes?
So you know how originally we started with f of x?
Mhm.
Can we do the Fourier series with f prime of x
Mhm.
in this case? So that we can do it. Are you talking about differentiating the Fourier series itself or the original function f of x?
So what should I take the derivative of?
I guess just in this case f of x.
So I have this series, right? And I want to compute f prime. Right? So how can I compute f prime?
Like the
Yes?
Multiply multiply everything you got in the summation there, and then take the derivative of that, and have that be the summation of the.
Yes, I have to take the derivative of the whole thing, right?
Yeah.
What is the next step?
Present it as the differential series, find it, then take the derivative with respect to sign.
Yes. Can you say at the back of the paper, please? So you have to take the derivative of the whole sequence, right? You can take the whole derivative of each one. So derivative of f will be n is going from 1 to infinity of 4 over n pi to the power 3, 1 minus 1 to the n sinus n pi x prime. All right? It's clear. For instance, this is as simple as this. So suppose that you have f is sinus of pi x plus sinus of 2 pi x, right? Suppose that the series has only 2 components. So if you want to take the derivative, you just have to take the derivative of the sinus. All right? Example. So you have f prime of x will be sinus pi x prime plus sinus of 2 pi x prime. All right? So in order to take the derivative of the whole series, you take the derivative of each term and you take a sum, right? It's clear? So let me explain it in a clear way. So I'm going to write this in the form that we are more familiar with. So I have what? I have fx is going to be the series when n is going from 1 to power 3. When n is 1, this is going to be 1 minus 1 to the power 1 sinus of pi x. Right? This is n is equal to 1. And then I'm going to have 4 over 2 pi to the power 3, 1 minus 1 to power 2 sinus of 2 pi x plus 4 over 3 pi to power 3, 1 minus 1 to power 3 sinus of 3 pi x. And you continue this. So this form is the shorthand of this sum, right? So you're gonna let n to be 1, 2, 3, 4, 5, and you're gonna replace n to be 1, 2, 3, 4, 5 into the sinus, all right? And you take a sum. So fx will be 4 over n to power 3, 1 minus 1 to power 1, because I replace n to be 1, sinus pi x. So here n is 1, so you have sinus pi x. The second one is to replace n to be 2. So you have 4 over 2 pi to power 3, 1 minus 1 to power 2, because n here is 2, and you have sinus of 2 pi x, right? And then you want to replace n to be 3, so you have 4 over 3 pi to power 3, 1 minus 1 to power 3, because here I replace n to be 3, and I'm going to replace n here to be 3. So here I have sinus 3 pi x, and I continue this infinite sum, right? So here I have a sum of all of the function of x. What I do to take the derivative is to take the derivative with respect to each guy of the function of x, right? So I have 1 minus 1 to the power 1 sinus of pi x prime. All right? And I'm going to take the derivative of this guy, because you have just a sum of all of the function sinus, right? So you're going to take the derivative with respect to that guy. So I have 4 over n pi 3, 1 minus 1 to power 2 sinus of 2 pi x prime, plus down here I have 4 over 3 pi to the power 3, 1 minus 1 to power 3 sinus of 3 pi x prime. All right? It's clear? Questions?
Wouldn't every even numbered one equal 0 in
Yes.
this case?
So all of the even will be 0. So this guy is 0, this guy is 0, and the odd one will become 2. Right, so this is 2, this is 2. All right? Questions? You have a sum of function of sinus, of the form sinus. You take the derivative by taking the derivative on the sinus. Right, so now let us try to take the derivative of sinus n pi x. So the derivative of sinus n pi x will give you, this one will give you n cosinus of n pi x, right? So this is going to be 4 over n pi to the power 3, 1 minus 1 to the power n. All right? I keep everything. I just replace this derivative by n cosinus n pi x. Yes, questions?
Why is it n cosine n pi x instead of n pi cosine n pi x?
N pi, thank you. Thank you. Can you say at the back, please? All right. So when you take the derivative of n pi x prime, you get n pi cosinus pi x. Right? Now, I want to take the second derivative of this guy. So one remark, because here I have n pi, here I have n pi. So what I have at the end is n is going to, from 1 to infinity, of 4 over n pi to the power 2, because I'm gonna remove this from this, right? 1 minus 1 to the power n, cosinus of n pi x. Right? I'm gonna take the derivative of f by taking the derivative on all of the sinus function. That gives me n pi cosinus n pi x. All right. Now I have this n pi x here. I have this n pi x here. This is why I remove one power of n pi. So I reduce. This is power 3. So here I have power 2. Questions? Now suppose that I want to take the second derivative. What should I do? So this is f prime. I want to take the f's prime prime. Yes, can you say at the back of this? Now I want to take the second derivative, which is f prime prime. So to compute f prime prime, what I do is I'm gonna take the derivative in cosinus again. Right? So I have f second of x will be n is going from 1 to infinity of 4 over n pi square 1 minus 1 to the power n, and I'm gonna take the derivative of cosinus n pi prime. All right. So once you have the series, you can take the derivative on a cosinus function. It's clear? Now I'm gonna take the derivative of cosinus n pi, which is n pi minus sinus. All right. So here I have the sum with n is going from 1 to infinity, 4 over n pi square, 1 minus 1 to the power n, and here I have n pi. Here I have a minus sinus n pi x. All right. So I keep everything, except that here I replace the prime by minus n pi sinus. All right. So here I have an n pi, here I have n pi, so I'm gonna put minus, I put the sum when n is going from 1 to infinity of minus 1 over n pi, 1 minus 1 to the n, sinus n pi x. Yes?
Shouldn't it be 4 still, I think?
Yeah.
Thank you. Can you sign at the back of this? All right. Now I have f prime already. If I want to compute f second, I'm gonna take the derivative with respect to the cosinus function. All right. So the derivative of the cosinus function will give me minus n pi sinus n pi x. It's good. Now I'm gonna. I have n pi here. I have n pi squared here. So here I have only 1 n pi. The minus here goes here, and here everything else is the same. Yes?
We can move that negative sign to the 1 minus negative 1 at the end.
Yes,
though, and give
yes,
it a
it's the same.
easier to read.
Right. So you can put it here or you can put it here. All right? It's the same. Yes?
So is there basically like just a pattern as you take the derivative of each one, basically you're decreasing your power?
Of n pi is decreasing.
And then, yeah,
Yes.
based on the function or the cosine or the sine, you get a negative across it.
Right. Yes. Can you sign at the back of the paper, please? So every time you take the derivative, you're gonna reduce 1 power of n pi here. But what can you see from this computation? Any remark?
Continuous.
Yes, of course it's continuous, but I want to compare the form of f second and f. So what can you see?
It's the negative, the 1 minus 1, and that's negative there, that's positive there.
So I want a deeper point, yes?
The alternate between sine and cosine,
Right.
every time we differentiate, and the n pi at the bottom reduces by 1 power every time we differentiate. So
Yes, and you?
That is the same function with a different coefficient in the front.
Right. Can you both sign the back of the paper, please? All right. So you can see one very interesting thing is the following. After you differentiate 2 times, here I have the same sinus, except that the coefficient is different. Right? It's clear? So this is the key point. So you differentiate twice, then the function sinus return to the function sinus. Of course, you have to multiply with all of the coefficient that sinus n pi is producing. But basically, it is the same basis, right? So f, remark, f and f second have the same basis. Basis which is sinus of n pi x. And this is good. Alright? So the remark here is that after you differentiate twice, you come back to the same basis. The first basis is sinus because cosinus are all 0. So the first basis is sinus. You differentiate and you fall into the basis of cosinus. But now you differentiate another time, you come back to the basis sinus n pi x. All right? And this is very important. Because, right, in general, I'm gonna try to generalize this picture as follows. So suppose that we forget about all of the coefficient. We're gonna do it with the general coefficient, right? So we have fx is the sum when n is going from 1 to infinity of dn sinus of n pi x. All right. So suppose that we forget about the form of all of those 1 over n pi square or whatever. So we call it a number Pn. Now let us see what is going on if we take the derivative twice of this function. So the first time I take the derivative is going to be n is going from 1 to infinity bn n pi cosinus of n pi x. All right? So the first one I differentiate. I'm gonna get 1 factor n pi. All right? So this is going to be integral from 0 to infinity of bn times n pi of cosinus of n pi x. All right? So the first time we differentiate, we get an n pi. Now, the second time we differentiate, we're gonna get Bn n pi, but we're gonna take the derivative of cosinus of n pi. All right? And this gives me 1 to infinity of Bn of n pi minus n pi sinus of n pi x. Right? So you differentiate the second term, the cosinus n pi will give you minus n pi sinus n pi. So what you get is the integral from sum when n is going to 1 to infinity of Bn n pi squared with a minus. And then you have sinus of n pi x. Basically, it is the same series. The only difference is this factor. Right? So the Bn will become the Bn. The sinus will become the sinus. The only difference is this factor. All right? Yes?
The coefficient there, the Bn times the n pi squared and whatnot, would that be essentially the amplitude of the waveform?
Yes, I'm gonna come to that point in a second. Can you stand the back of the paper, please? Right. So I explain again. So the first thing is fx is the sum when Bn sinus n pi x. You differentiate the first term, you come to the cosinus, but you have to multiply with n pi. The second derivative, you come back to sinus, and you multiply by minus n pi squared. All right? And the difference, the only difference between f second and f is this factor. And this factor, we call it eigen values, similarly to linear algebra. So in this action, the second derivative is called an operator. So taking the second derivative is an operator. Right? So the fact that you are taking the second derivative, you call it an operator. All right? And the operator here, I denote it by L. Right? So the operator that you have is LF, is F second. Right? The whole thing that I'm doing, the process that I'm taking the second derivative, I call it an operator. And I name it by L. So I am saying that LF is the second derivative of F. This is the operator. All right? So in all of those processes, what my observation is that, okay, sinus of n pi x second is minus n pi squared sinus of n pi. All right? So in the whole process, what I can see is that, okay, the second derivative of sinus n pi is minus n pi squared sinus of n pi. Right? So which means that I'm taking the operator acting on sinus of n pi, and I get minus n pi of the sinus of n pi. All right? Yes?
So we've been taking just from, say, -1 to 1 for all of this, but if we were to show the entire continuum of these waveforms, as n increases, the amplitude would increase linearly, right?
Mm-hmm. So here we only consider that these are -1 to 1, right?
Okay.
But I'm gonna, in the next lecture, I'm gonna show you how to do this from minus L to L. Basically, you have to divide by L here only.
All right.
Yes?
Is that supposed to be minus n pi squared?
Thank you. Can you sign at the back of the paper, please? Now the function phi n, sinus n pi, I call it phi n. And this guy, I call it lambda n. So what I have is L of phi n is lambda n phi n. All right? So I just call this function to be phi n, and this value to be lambda n. What I have is lambda n is equal, L of phi n is equal to lambda n phi n. This is so this has a very similar form with eigenvalue and eigenfunctions, eigenvectors in linear algebra, right? But let us try to finish this formulation. All right. So again, let me explain again. So the fact that I'm taking the second derivative is I define that to be an operator, right? So this is my operation. So I'm gonna take the operation of taking the second derivative of the function on this function f. The operator will be f second. Now, if I take it on the sinus n pi, it's going to return back to sinus n pi, except that you have one factor minus n pi squared, right? So I call it lambda n, and this sinus I call phi n, right? So now I gotta go back to that formulation. I have fx is the sum when n is going from 1 to infinity of bn of sinus of n pi x. All right. This I just name it to be phi n. Right. So this will give me n is going from 1 to infinity of bn phi n. All right. So what I found here is that when I take the second derivative, I got phi n, lambda n times phi n, right? So when I take the second derivative, I'm gonna get the same thing except an extra factor, which is lambda n. All right. So this is the extra factor that we have after the second derivative, right? So which means that the lambda n is called eigenvalue, and phi n is the eigen function. So does this looks familiar with you in the class in linear algebra? You have something similar, right? So in linear algebra, you have something like this. You have a matrix. All right. So in linear algebra, you have a matrix A, for instance, 1, 2, 3, 4. All right. So this is a 2 by 2 matrix. 2 by 2 matrix. And this matrix is invertible because the determinant is not 0. So then there will be lambda 1 and lambda 2 and two vectors v1 and v2. So let me call it x1, x and y. X to be x1, x2, and y to be y1, y2. All right. Such that a of x is lambda 1 x and a of y is lambda y2, right? And lambda 1 and lambda 2, they are called eigenvalue. And x, y, they are eigenvectors. Basically, this is the first homework that we have. All right? So in linear algebra, if you consider a matrix which is invertible in the sense that the determinant is not 0, and this is a 2 by 2 matrix, you can find two numbers, lambda 1 and lambda 2, and two vectors, x and y, such that ax is lambda 1 x and ay is lambda 2 y. So lambda 1 and lambda 2, they are called eigen values, and x and y, they are eigen vectors. Here it is the same. So here you don't have a matrix anymore, but you have an operator, which is the action that you take the second derivative, right? So here the matrix A will be replaced by the the operator L. So L of f will be the second derivative of f, but the same thing happens. So you also have eigenvalue and eigen. Here this is a function, so I don't call it eigenvectors anymore. I call it eigenfunctions. So the same thing happens. If you take the operator L on this phi n, which eigenfunction, you're going to have lambda n phi n. And this fact is powerful because when you have fx is this sum, when n is going from 1 to infinity, you have bn sinus n pi x. You take the second derivative, all right? When you take the second derivative, you're going to have the same series except a new factor, which is the eigenvalues, all right? So here, because I have f second, I'm going to write Lf is equal to sum when n is going from 1 to infinity of bn lambda n phi n. All right? Questions? So in this case, the sinus are eigenfunctions of the operator L, which is the second derivative, and the lambda n is minus n pi square, which is the eigenvalues of this operator. And of course here everything is considered on minus 1, 1 because we are from the beginning on this interval. All right? So if you have from minus L to L, you have to divide this by L, and you divide this by L, and here you have to divide this by L. But I'm gonna come back to that to have a more precise expression for that kind of thing. Questions? It's clear? Right. So so in this case, we say that phi n is sinus of n pi x, and their eigen function, and lambda n is minus n pi square. Their eigenvectors and eigenvalues of the operator. All right. In this case, we say that this is an eigenvalue, eigenfunction, and this is an eigenvalues of the operator L, and this is and we are on minus 1 to 1. All right. So my question is, can we have? I mean, if you have the other type of operators, do we have eigenvalue and eigenfunctions?
If we want.
Now, the operator here is something that we. So the operator is LF is the second derivative of f, right? My question is, what if I take the operator L to be f second plus f? Do we have eigenvalues and eigenfunctions? Do we have this kind of behavior, right? So you have lambda phi n is lambda n phi n.
Yes.
Why? Yes, the answer is yes, and the reason will be in the next lecture. All right? So in the next lecture, we're going to try to find, we're going to consider operator of the form not only f second, but it could be f second plus f or f second plus f prime. And we're going to try to see for which one we have eigenvalues and eigenfunctions, right? Right. So this is lecture 2. Any questions on this? So, lecture 2, which is Boundary value problem. So first, I'm gonna define what is a differential equation, right? Differential equation. A differential equation is an equation in which you have a derivative, right? So we have u prime of t plus sinus of t is 0, and we try to find the function u. All right. So this is a differential equation because we are trying to solve for the function u, right? So we try to find a function u such that u prime of t plus sinus of t is 0, and then in this equation, there is one derivative, a derivative. All right. So in this equation, you solve for one function, and in the equation you have one derivative. This is called a differential equation. All right. Now, example. Suppose that you try to solve ut squared plus is equal to x squared plus x power 4. Is this a differential equation? Anyone? No? Why? Right. So here, this is not a differential equation because there is no derivative, right? So we find a function but there is no derivative. All right. So the unknown in this equation is the function u. You have to find a function u. Ut squared such that here you have t x squared plus t squared, right? So you have two variables. So this is t squared plus t to the power 4. So you have to find the function u that satisfies this equation, but there is no derivative. Then this is not a differential equation, right? Questions? It's clear. So example number 2. So you try to solve x to the power 3 minus 1 is 0, right? So is it the differential equation? No? And what is it?
The cubic.
Yes, it's a cubic equation, but for instance, this is also a cubic equation. So what is this, the name of this? This is an algebraic equation, right? Algebraic equation. Since the solution is a number. Since the solution is a number. All right. So for a differential equation, you have to look for a function, and in the equation you have different derivative, right? Questions? Right. Now, suppose that I want to solve this equation, but I have a constraint, and for instance, suppose that I want to solve this. I want to solve u prime of t plus ut squared is equal to sinus of t. And suppose that I have u at 0 is equal to 5. So what is the name for this constraint? What is the name for this condition? Yes?
Initial condition.
Initial condition. Can you say at the back of the paper, please? So this is called the initial condition. All right? Now, suppose that we have two conditions on two sides. I want to solve this equation. but I have u0 is equal to 5, u1 is equal to 9. So what are the condition? So what is the name of this condition? Yes. Boundary condition inside the main paper, please. So if you have two, this is boundary condition. Right? So if you have only one, this is the initial condition, and if you have two, this is the boundary condition. All right? And this problem is called a boundary value problem. All right? So a differential equation in which you have two boundary conditions is a boundary value problem. Questions? That's good. Now you have a partial differential equation. Partial differential equation. So a partial differential equation is an equation in which you have, any guess?
Partial derivative.
Well, multiple variables, like input variables. So you want to take it with respect to x and y. There's two different derivatives in that case.
Yes.
Can be represented as a combination of multiple functions.
No. So can you two sign the back of the paper, please? So, so basically, in a partial differential equation, you have partial derivative. This is the most important, right? An equation, you have, so an equation involving partial derivative. All right. So for instance, you have to look for a function f, or a function u. So such that this plus dx of u dx is equal to sinus of 5x. So this is a partial differential equation because we have to look up for a function u, and this involves partial derivative in t and the partial derivative in x. Right? So we have partial derivative in t and x. Right? So what is a partial derivative? Anyone else? Anyone else? Yes?
A derivative in one variable assuming that the others is a constant.
Yes, can you say? Can I back number 5 of this? So if you have a function of only one variable, the derivative is just a derivative, right? So if ut is a function of one variable, right? So then u prime of t is the derivative of u in t. So if you have a function of only one variable, then the derivative is just the derivative, right? So there's nothing extra on this. But now if utx is a function of multivariable, then dt of u is a partial derivative and dx of u is also a partial derivative, right? So the difference between partial derivative and a normal derivative is that the partial derivatives are derivatives for functions that are multivariables, and if you have only one derivative, you only have a derivative. There's no partial derivative, right? So which means that, okay, when you change from differential equation to partial differential equation, So what is the main change? Right? So from the beginning, so here I have a differential equation. So this is differential equation. So here I consider a differential equation, and here I consider a partial differential equation. So what is the key difference in the two equations? Yes?
Two variables.
Sorry?
There are two variables in
Yes.
In the first one, you're working in R2, and the second you're in R3.
This is in R1.
Pardon?
So T is in R, right? So this is an R1. Right, so
T
here-
is known, but the function acts as the second axis if you're trying to make a graph of it.
Yes.
So
Yes.
the function is now dependent on two variables, so you've got basically an R3 space.
Right. So can you both stand the back of the paper, please? Right. So the key difference between the two equations is what? You change from derivative to partial derivative, and you change from a function of one variable to multi-variables, right? So you change from one variable for differential equation to multi-variable. Right? For partial differential equation. So the solution in the differential equation has only one variable, and the solutions in partial differential equation has several variables. Yes?
In that partial derivative there, what does it mean when there's two x's?
Yes. So what is the 2x here?
Yes.
Who knows? Yes.
You differentiate with respect to x.
Yes, but what is the meaning of the second 2xx?
You differentiate with respect to x and then differentiate again with respect to x.
Yes, can you sign at the back of the paper, please? Right, so the second derivative here, so the dxx here, meaning that you take this, the derivative in x twice.
Second partial derivative.
Right, so basically dxx of u will be dx of u. Right? Now, what is dxt? Yes?
You take the partial with respect to x, and you take another one with respect to t.
Can you say at the back of the paper, please? So here you have partial derivative with respect to x, and then you have a partial derivative with respect to t. You take the partial derivative with respect to t first, and then to x, right? Other questions? It's clear? So basically, the key difference between differential equation and partial differential equation is that you are working on function that are multi-variables, right? All right, so so now let us try to solve one equation which is so the Laplace equation. So before studying the Laplace equation, we consider Laplace operator, right? So in one dimension, so suppose that u is a function of ut. L of u will be u second. That's it. It's a minus. All right. So this is the Laplace operator. So in several books, you're gonna see that here they have a minus, but suppose that in this class we don't have minus. It's the same. You have to change the sign only, right? So the Laplace operator is the simplest action that we have done before, which is to take the second derivative of a function, right? So this is called the Laplace operator. So now suppose that you have u is a function of u of x1, x2, x3. x2. The Laplace operator will be the partial derivative with respect to x1, but you take 2 times. And then you take another partial derivative with respect to x2 2 times, right? So L of u will be the x1 of u plus the x2 of u. All right? It's good. So the Laplace operator for the one variable case is the second derivative. But if it's multi-variable, you have to take the second derivative with respect to all of the variables and you take a sum, right? And so suppose that you have u is u x1, x2, xd. So here d is the dimension. D can be 1, 2, 3, etc. So the Laplace operator will be the x1 of u plus the x2 of u plus the xd of u. So the Laplace operator of a function of d variables will be the second derivative with respect to x1 of u plus the second derivative with respect to x2 of u plus the second derivative with respect to xd of u, right? It's clear? So you just take all of the second derivative and you take the sum. So now solving Laplace equation in 1D. So suppose that we want to solve uxx is equal to 1 for x is going from 0 to L, such that u at 0 is 0 and u at L is also 0. Right? So in the next step, so after we define the Laplace operator, the first step we want to solve is to solve the Laplace equation in 1D, in one dimension. So in one dimension, I only have uxx is equal to 0, right? Or u second. This is u second is equal to 0. With u0 is 0 and ul is 0. So what is the name of this equation? Anyone else? Yes?
Second order homogeneous?
Second order homogeneous
Differential equation?
differential equation. Not enough. I want something else. Yes?
Is it a boundary value problem?
Yes. And this is. So you combine both, right? So
Oh,
this is second order differential equation with constant coefficient, homogeneous, and then this is also a boundary value problem. All right? Can you both sign it back on the paper, please? So this is a boundary value problem. So this is second order because you have second derivative. This is homogeneous because here you have 0, right? So this is second order. Second order. And this is linear, right? Yes?
It's second order partial, right?
This is second order differential equation because you have only one variable. So second order differential equation. This is linear, right? Because here you have 0, so this is homogeneous. This is homogeneous because on the left hand side, on the right hand side you have 0. This is linear because you have only one, the second derivative. This is second order, and then you have boundary value problem. Because you have two boundary condition at 0 and L, right?
Do we go on ordinary if EQ?
So this is our ordinary differential equation.
Okay.
Yes. So sometimes you can call differential equation by ordinary differential equation. It's going to be the same. But people prefer ordinary differential equation to make a clear difference between ordinary differential equation and partial differential equation. All right. Now, I want to solve this problem. I have the second derivative of u is 0, u at 0 is 0, u at L is 0. So how can I solve it? Anyone? Yes?
And so you're saying the second order of differential equation equals 0, so couldn't you just take the integral twice?
Can you say the back of the paper, please? So you have u prime to be 0. All right? Because u second is 0, I can take the integral on both sides, and this gives me u prime is equal to a. All right? So I just take the antiderivative of the function 0. So the antiderivative of the function 0 is a constant, which is a. All right? Now I'm going to take another antiderivative of the function a, which is, then u should be ax plus b, right? It's clear? All right? So u second is 0, which means that u prime has to be a constant. You take integral on both sides. So the antiderivative of the function 0 is a constant a. Now I'm going to take the integral on both sides. So the antiderivative of the constant a is ax plus b. Right? So what is the next step? Yes?
Could you just plug in the boundaries?
Yes. Can you sign the back of the paper, please? Right? So the first step is to try to find a function u that satisfies this equation. Now I'm going to check with the boundary condition. Right? So u0 is 0, meaning that, so let me write here. So this is boundary condition. All right, so you have u0 is 0, meaning that a times 0 plus b is 0, so b has to be 0. Right? Now I'm going to use the boundary condition. Because u at 0 is 0, I'm going to replace 0 here. So I have a times 0 plus b is 0. So b is 0. Right? So u has to be ax, because b is now 0. Now the next step is I'm going to replace the second boundary condition. Right? So ul is 0, meaning that a times l is 0. So a has to be 0. So basically ux is 0. So this is the only solution that we have for this equation. Function is 0. Right? I explain again. This is the most, the simplest boundary value problem that we have. We have a Laplace equation in one dimension with two boundary conditions. U at 0 is 0 and U at L is 0, right? So because U second is 0, you can take the antiderivative of U, and this gives you U prime is equal to a constant A, right? Now you take another antiderivative of the constant, you have AX plus B. Now you're gonna replace this into the two boundary conditions, right? So you have U0 is 0, meaning that B has to be 0, and then the function U is now AX. Now UL is 0, which gives you A is 0. So the only solution that you have for this Laplace equation is 0. All right? Still have questions? It's good. So this is the simplest equation that we have. And to solve this equation, we don't need any special techniques. We still have 2 minutes, right? All right, so now let us try to solve one quick example. You have Ux, X is 0, And then ux at 0 is 10, and ux at L is 20. So this is one example that we have in the lecture notes, right? You have the Laplace equation. This is still a boundary condition. But the boundary condition is different because here you have derivative. Right? So in this boundary condition, we have derivative in the boundary condition. All right? So in this boundary condition, we have derivatives. It is still okay because it is still a boundary condition. It's the value of the function or derivative of the function or the second derivative of the function, and it's at the point on the boundaries. All right? So how do we solve this equation? Yes?
The same way, it's gonna be that u of x is equal to ax plus b, and then you take the derivative and then plug in the boundary.
Can you stand at the back of the paper, please? So you're going to solve it the same way. U second is 0, meaning that u will be, u second is 0. So you do the same method that we have over there. So we have u is ax plus b. So now we're going to plug this into the two boundary condition, and we're going to check that. So we're going to meet again on Thursday.